it, I always start with my axis of symmetry. When it's in standard form, I get my vertex and go. Now, on the other hand, when I start with vertex form, I know where I'm going to start at. I know where my axis of symmetry is going to go through. And then from there, it's very simple to pick points on either side. When you're in intercept form, you have to remember that you have to find the axis of symmetry, which hopefully wasn't so bad. You would just have to take the midpoint. Once you get the midpoint, then you have that, find the value of y, and it drops into a column very similar to this. Okay? Yes, sir? Sure. Would you mind reading it to me? Plus 4x minus 2. Okay. So this one here, that's going to give me an axis of symmetry, opposite in b over 2a. So it gives me axis of symmetry at 2. Okay. I plot my axis of symmetry at x equals 2, which means my vertex is going to have a x coordinate of 2. Straight-ish. Okay. So when I take the value of 2 and I substitute in, what's up, Twig? What's 2 squared? 4. 4 times negative 1. So I have a negative 4. 4 times 2? 8. So I have negative 4 plus 8. Subtract 2. That puts my vertex at 2, 2. My A value in this case was what? It's negative 1, which means what direction is this going to go? It's going to go down. It's going to go down like a crown. Okay? Now, my next point to either side, left or right of it, are also pretty easy to use. I would choose my next 2 points to be at when x is 1 and when x is 0. So if I use 1, what's 1 squared? It's 1. So I get negative 1 plus 4 minus 2, and I get 1. So here's 1 point, which means the symmetric twin is on the other side of it, right there. Okay? When you are in standard form, the shortcut that's really nice to pick up on is your value of c will always be your what? Y-intercept. So here I know that my y-intercept is going to be at negative 2. And that happens to be my next one down. There we go. Okay. Which leads us to being what we're going to do next. Oh, that went loud and crazy. Which leads us to y and how we're going to set up and work with factoring. I know, right? Factoring is a way that we're going to take quadratic equations, we're going to break it down into what are called terms. You're going to see me say, or hear me say the word terms a lot, and I'm always going to put my hands into like the parentheses more often than not when I say the word terms, because I want you to understand that a term is going to be something in parentheses. When we factor stuff, it generates terms. Terms, therefore, can be set equal to 0 to give us zeros. And you saw that yesterday when you were graphing things that were written in that intercept form. Intercept form is nothing more than a factored quadratic. Factored quadratics are written in intercept form, but you got your x-intercepts. Your x-intercepts were your zeros of the function. This whole idea of terms and zeros get into the whole, what's called the fundamental theorem of algebra. Basically, is what we spend a lot of time on here after we get through quadratics and stuff. We get to polynomials and things like that, where basically it means that whatever nth degree polynomial you have, nth degree just means is it a squared, cube, quartic, whatever, fourth degree, fifth degree. If you're a squared term, you have up to 2 possible zeros, 2 terms. They may be the same term, they may be an imaginary term, they may be a non-real term, they can be anything like that, but you all get the idea of terms. So what we're going to be able to do here throughout the course of the next couple of months or so is we're going to be looking at how algebra, this fundamental theorem, allows you to work with zeros, and terms to work back and forth between polynomials. And then it's all the same process. But it comes down to the idea of, can you factor? And when I talk about factoring, I know that each and every one of you guys have seen multiple algorithmic ways of doing that. I use a weird term, algorithm. You guys know what that means? What's that? No. An algorithm is kind of like a way to do a problem. Here's a tried-true process to set this up and do it. It's what you guys like. Just tell me how to do it, and I'll do it. Right? An algorithm is a process by which we're solving a problem. In math, we have all these different algorithms, for everything. Well, factoring over the course of the past 10 years or so has gotten to be one of those, well, let's teach them this, let's teach them that. It's kind of like with multiplying and adding, you know, the methods people use, that box method, the fence, all that stuff. But what bunnies multiply, good call. What I like to fall back on when I talk about factoring is the old-fashioned way that I learned, and I know back in my day, we actually did the same process over and over and over again. There's nothing wrong with what you guys have learned. The way that I have done it in the past, though, I found that if students get accustomed to replicating this process, it's easier on them. You know, and Naka was just talking to me earlier, he goes, is this stuff a little bit easier than what we were doing? Like, yeah, because there's a specific way to do these next problems for the next phase of this unit. If you follow the process doesn't change. The complexity of the numbers might, but the process is the same. And I know that you guys are perfectly fine with the replication process. So, how are you? I'm doing great. Good to see you. There you are. So here's what I learned. Back in my day, I did this. What times what is negative 28 that adds together to get negative 12? Basically, what I'm looking at here are what are my multiples of 28, playing around with the signs to get to the summation part. And you've already said, I mean, a lot of this stuff is quick. You guys remember this from back in the day. Now, if you forget, you know, your factors are 1 and 28, 2 and 14, 4 and 7. Which combination of those two with the signs give you the negative 12? Which one's positive, which one's negative? Yep. So this is the case. You have negative 14 and a positive 2. So what happens here a lot of times is that it's just a reminder of what does it mean? If you're multiplying two terms together and your last term winds up being negative, that means one of your terms has to be negative. Those two. Negative. If the middle term happens to be negative, that means the larger of the two is negative, because when you're adding them together. Whereas if the middle term was positive, the last one was negative, then you have to be a bigger term. These are things you've all seen. Yes, ma'am? No, if there's another way that if you've done the box method or whatever, I'm not saying one way is better than the other. Because eventually, if you do wind up with fractional things, it's much easier to work with fractions with a method like this than it is with some of the box stuff. We're not hitting. Don't worry. Don't freak about fractions yet. We will see them at a point, and you'll be, oh yeah, that's why Murphy said this way is going to work a little bit. If you have another method, I'm not going to say no. Okay. So this means that your terms of this problem wind up being x minus 14 and an x plus 2. Did it matter to which side got the negative 14 or which side got the 2? No, it doesn't matter, because the order in which you multiply things out doesn't matter in math because of the what property? Very good. Commutative property, multiplication. All right, order doesn't matter. Now, one of the things you guys could do then to check to see if you were right and not just a doofus, you could FOIL all that out, remember? First, outside, inside, last. So you could do the FOIL, first, outside, inside, last, otherwise known as Billy binomial. That's Billy binomial. which means a kid that got down to, I think I yelled done, and he goes, because he had like 3 left. And that, so, it was seriously like 3 years ago. I don't know, right? I have to think of it. But yeah, the reason that I do that, and I do this every year when we talk about factoring, is because if you understand your math facts, factoring is super, super, super quick. Okay? That's what I was trying to get at. You don't have to finish this now. Go ahead and grab the rest of your stuff out real quick. Let's talk about why and how some of these things put together and stuff. Like I said, a lot of this stuff today is total review. I know that all of you guys have factored at least once or twice in your life. So, and I love scaring the out of you guys when I'm done. Right across. As you write it going across, you go down it. So when you when you're done here, I come back to my 3 line. If I had a multiply on each side, I would all right. So back to this then real quick. Same idea. Same idea. X squared plus 4x minus 21. What times what is negative 21 that you add together to get 4? Now, 7 and what? 7 and 3. Now, for a lot of these things, do you really need to constantly rewrite out that, unless you rewrite out that t-chart or however you do that? Or can you look at it and say, oh, I know that my terms, things in parentheses, are going to be, I just know that that's what's going to happen. Do you need to put them in? Do you have to write it out and write them all through? If you want to, by all means. Ms. Mitchell, which way do you do it? Do you do it? You said you're doing it differently. Are you doing that box?
No. I just use like
it's guess and check. That works out fairly decent when your first coefficient isn't 1. But I'll show you a method that works. It's very, do it this way, and it will force you to it, and sometimes it's a little bit quicker. By all means, guess and check, and there's nothing wrong with it. There really isn't. It doesn't bother me whatsoever. Okay? Just saying that, try it, especially when you get coefficient not 1. What changes to the problem if it had that? What do you solve for? Your zeros. And we learned yesterday when your equation looked like this was what we called intercept form, which means the x-intercepts were when each of the terms were set equal to 0. So you had zeros of this function were located at -7 and 3. When you guys did the that pretest the other day, we had a factoring problem right up in front where a lot of you guys, I think it just said factor, or no, sorry, it said solve the equation. Okay, it said solve the equation. You guys wrote down, if it was like this, you just said your answers were 7 and -3, as opposed to putting the terms together first and then the zeros. Okay. It's the terminology of what is a term versus what is a 0. And that's where we spent a little bit more time talking vocabulary like that. Oh, we did that one. All right. What about that? 2x squared minus 2x minus 24. Correct. Because your first rule of factoring is to have what? Yeah. Your first rule of factoring always starts with a G and ends in a CF. That's what I'm here for. That's what I'm here for. So whenever we have something that is simplifiable, whether it's a quadratic with 3 terms or sometimes quadratic with 2 terms, you always want to see if you can figure out what the GCF is first. In this case, what's the GCF? 2. So I factor out a 2. Then I'm left with x squared minus x minus 12. So what times what's negative 12 you add together to get negative 1? Negative 4. Okay, so we have 2. Now, when this says y equals, that means you're going to find the 0 for it. When you factor out a GCF of a 2, does that have any bearing upon the 0? No, it doesn't. It has no bearing upon that whatsoever for the 0, because remember, if you are finding zeros, you're setting your terms equal to 0. So if you move your GCF over, what's 0 divided by 2? 0. GCFs are just scalars. They have no bearing. You guys remember what a scalar meant? A scalar just means it's multiplying, you're distributing out to make something look larger than what it needs to be. Okay? It's like wearing, extra muscles underneath your shirt. Right, Ryan? That's what you do. Right? That's what you do. Making fun of you, but it didn't work. Because you're trying to deflect the shins. Because we all know Shifty is just ripped. Zeros would be there. Okay. We're not going to have any homework tonight that has zeros. I'm just kind of throwing that in today, so when we do it tomorrow, you'll be like, oh.
No.
What happens when you don't have a b value? The b value equals 0, okay? So this, in essence, is the exact same thing as saying x squared plus 0x minus 16, which really says what times what is negative 16 that you add together to get 0. Okay. This, like we were saying, it's your plus or minus 4. So what happens here is that this is what we call a special pattern. Yes, sir. Yeah, I'm getting to where you're talking. I'm right about where you're about to talk here. Is when you see 2 terms, if the first term is a perfect square and the last term is a perfect square. Remember what perfect squares mean? Yeah. Yeah, square root, you get a nice number, exactly. And the symbol in between them is subtraction. This is what we call a difference of squares. Difference of squares allows you to just go take the square root of both sides, put a plus minus, and you're done. And it works out clean. Now, if you had something that looked like this, though, is the first term a perfect square? Is the last term a perfect square? Is that symbol in between them subtraction? That means this is not factorable. What times what's positive 81 that you add together to get 0? Nothing. Okay? So this is not factorable. Yes. Excuse me. Too many carrots are in flex. Right. It's better than eating a bag of chips. Even though I would love to have a bag of chips. What's that? I don't think so. We go through like 4 or 5 pounds a week.
That's probably not.
All right. What times what is 9 that you add together to get negative 6? Negative 3 and 3, or is it? Well, hold on. 2 things that multiply to a negative that add. I'm sorry. 2 things that multiply to a positive and add a negative, that means both terms have to be the way you said it was -3 and 3, I was wanting to make sure that you meant -3 and -3. That's why I was just trying to make sure you were finding that out. Now, you guys probably saw this last year when you had, well, let me ask you this. The way that I call this, those two terms, parentheses, are the same. Agree? So what I call that is junk times junk. Junk times junk is junk squared. Okay? Junk squared, yes, ma'am. Junk times junk is what I call junk squared. Now, what happens though is, for those of you guys that had said, this does not equal that. It's killing puppies. What? Exactly. You cannot distribute an exponent via a binomial because you kill a puppy. So remember, yes, ma'am. What's that? I know. I don't know if you put it up. I know I saw the poster. Is awesome. It's great. Remember, guys, and we'll come back to this again later. I guarantee when we see this again in a couple of months or a month or so when we go back to polynomials, some of you will kill puppies. Please, please, please think of the puppies. Okay. Let's factor with the first term that's not equal to 1. Now, what we've been doing all along is we've been looking at what times what was the last term that adds together to get to the middle. But really, in essence, what we've done, x. Yeah, I was just about to write that one down. Thank you. In essence, what we really did is we go back thinking about what the numbers meant. What's the coefficient of x squared here? The 1, right? So really, I was saying what times what was -21 that adds to 4. But really what I was doing was 1 times -21 was how much? And then I would say what times what was -21 that adds to 4. So this process that we've been doing doesn't change. We were multiplying our tails, A and C, to figure out what adds to B. What changes now is that the A value isn't a 1, here it is a 3. What's 3 times 10? 30. What times what is 30, positive 30, that you add together to get -17? You get the -15, oops, and a -2. Okay. Now, this is similar to what you were doing a little while ago with your guess and check stuff. Now, the way that I set these things up is that it is usually a step longer than normal, but it forces you guys to get the correct GCFs, the correct way to factor this out. Now, this is called a couple of different things. This is called either factored by grouping, or it's called split middle term. It all kinds means the same, because what happens here is I can rewrite this now as 3x squared minus 15x minus 2x plus 10. What I'm doing is I split that middle term into 2 parts. And now this is where this whole idea of factoring by grouping comes into play. Because how many terms are there in the quadratic? There's 4. Which means I can take my I can get the GCF of the grouping of the first 2 and the GCF of the grouping of the second 2. This is a method that I know you've seen, but it does take, it's just like an extra step, but I know that this algorithmic way of doing it forces you to the right answers. Okay? What we do is this. We throw parentheses around my first two, and I take the GCF. What's the GCF of 3x squared and a 15x? 3x, good. If I factor out a 3x, what am I left with now in my term? How much? X, just x, yeah. Okay. Now here's the trick. Notice how my two middle terms are both negative. What I always do here is that I force myself to remember that this third term is negative. I do a quick same change opposite. The reason that I do that is because now I need to remember to factor out that negative. Okay? It forces me to remember to take the negative out. What's the GCF of a 2 and a 10? It would be a 2, but by putting that negative, it reminds me, hey, knucklehead, take the negative 2 out. And that's how you're able to change the sign of that last term. Okay? By pulling out the negative 2, then, leaves that new term as x minus 5. So I've taken my GCFs, and now I'm left with, well, are these two the same? Yes. Write it down. What's left? And there you're done. Okay? It really, what you're doing here, you're splitting that middle term into what multiplies to the tails and adds to the middle. And then really, you take a GCF 3 times. You do it first, and then the second one should look like the same. And then really here, these two are in common. That's why we wrote it down here. So we really do 3 GCFs. It takes a second longer. It's probably close to what you were doing, but this forces you to see the patterns within the numbers. By all means, if you want to use yours, I have no problems with it. Okay? This is just, it's a little bit cleaner, and can you picture it if you had a fraction thrown into it? You can do like a 4/9, and you can pull things through, and it works out a little bit easier. Okay? So I know you've seen that. It's just been a while. Okay? All right. 6x squared minus 9x plus 5. Now let's see if we can factor it. We get 6x squared minus 9x plus 5, which means we're going to ask the question, what times what is positive 30? Add together gets negative 9. Well, what are your factors of 30? 1, 30, 2 and 15, 3 and 10, 5 and 6. So what's your answer? The answer is not factorable. Okay, that's not factorable. Okay. Now, will we eventually figure out methods to which to do that? Yeah. Quadratic formula. This would not be a good candidate for completing the square because the middle term is not even. We'll talk about that later. 2x squared plus 7x plus 3. Which means you're going to ask yourself what times what is 6. Add together to get 7. 6 and 1. 6 and 1. Does it matter which one I put first? No. It doesn't. I will say one thing, a little tip. If you have a plus minus when you're doing split middle term like this, put the negative first. All right, put the negative first. It's a little bit cleaner. So let's see here. We have 2x squared plus 6x plus 1x plus 3. What's your GCF of the first two? 2x, good. What's a GCF of 1x and a 3? 1. So 1. If nothing there, 1's there. Is x plus 3 the same thing in both parentheses?
Looks like it.
Looks like it to me. And we're left with? Hey, what would change if I had an equal 0 here? What are your zeros then? Negative 3 and negative half. Very good, very good. Okay. And that's where we're going. So I believe I already assigned something on the internet. Should probably find that. Do those, please. I know. You're welcome.